I guess we can get going. So, some of you may notice that I sent you another copy of slides about half an hour ago, maybe less. How's that? And there's the trivial changes. You kind of go through and think, oh, I should have said this, I should have added that. So they are in your email as an attachment, and you can call them up or look after them. But like I say, the changes are really minor. So wanted to do a lab tonight and wanted to do it on analysis of flavor. It's certainly an interesting challenge. If you think about what you want to do, you want to extract trace components out of really complex systems. I'll go through some of the challenges that make that extremely difficult. So doing the extraction, doing isolation, separation, identification is, like I say, a tremendous challenge. I want to spend some time with that. We'll do both aroma compounds and taste compounds. We'll spend by far the greatest amount of time on aroma compounds. They tend to be the greatest challenge, at least up front, in terms of the isolation. In terms of identification, then it gets to be more problematic to do identifications of taste compounds and aroma. But certainly from an isolation standpoint, total overall process, aroma compounds are much more complex. And so the idea is that extremely low amounts may be present. You talk about some compounds, parts per billion, parts per trillion. So we're talking about a needle in a haystack is a really good analogy. One needle in the haystack. How's that? So there's a problem with sensitivity, getting enough material isolated from the food. The compounds we're looking at don't have much in common when it comes right down to some physical parameter. What are we going to use to extract them from food? What's unique about flavor compounds that we can latch onto and say, I'm going to use this methodology to take advantage of this property? And there really isn't a lot to go on. There's a lot of similarity between flavor compounds, polarity, solubility, volatility, and so on. And so we have a bit of a problem having something, like I say, to hook onto and say, let's use this for extraction. Boiling point, I mentioned that already once before. Extremely broad range in boiling points. Volatility, would you say something that boils at 280 degrees centigrade is volatile? I suppose. It doesn't decompose. It does go into the gas phase. But it sure takes a lot of heating to get that vanillin out and into the gas phase, separated from the food by volatility methods. Hydrogen sulfide, minus 60 degrees centigrade. Okay, that's quite a range of compounds if you want to try to take volatility as a common parameter. And the same with solubility. If we're going to think about an extraction, solvent extraction of some kind. Well, limonene is oil soluble. Diacetyl butter is water soluble. So again, a tremendous range in solubilities. So there's really a difficult challenge in terms of finding something, like I say, that helps in extraction of a property. And there's always the problem that if we go ahead and extract all these things, what the heck is important? So there's an awful lot of compounds, volatile compounds in foods. Which ones are important? We won't spend time with which ones are important in this lecture. We'll do that probably in the next one. We're going to spend most of our time simply looking at isolation methodologies. And so let's go ahead and keep on going. Functional groups, extremely diverse, numerous. Again, if we could say they're all aldehydes, oh gosh, we could have some neat methodology for aldehydes or neat methodologies for sulfur compounds, but guess what? Flavor compounds cover almost every functional group you can think of. Again, well over 11,000 different compounds have been found to be volatile potential aroma compounds. And of course, they're distributed in complex, perhaps emulsified food systems. Water, proteins, fats, carbohydrates all make things difficult. And of course, they may be reactive, they may degrade on heating, or react with each other, react with the matrix, be pH dependent. So, like I say, there's a good deal of challenges that show up when we try to use this kind of a methodology. We do have some parameters we look at, though, or some principles that we tend to look for, take advantage of. To be an aroma compound, they must be volatile. So, okay, that's one that we look for, volatility. And if you go to lab tonight, we have quite a variety of methodologies set up for you. We'll show you how they work and how they apply to, like I say, our aroma or flavor isolation processes. Volatility, well, we can do a distillation. You'll see an apparatus called SAFE, solvent-assisted flavor extractions. So we're going to see it later, too. We can just simply put something in a bottle, close it up, allow it to come to equilibrium. The aroma compounds will go into the gas phase with some sampling of them. And you can stick a syringe down into that bottle, drop some gas phase, and simply put it into a gas chromatograph. That's nice, but not very sensitive. So, okay, we will only see the major components, and usually not the aroma compounds of interest to us. How's that? But so volatility, headspace sampling, ways to concentrate our headspace sampling, another methodology for concentrating. Like I say, we'll cover each of these methodologies. So volatility, we do take advantage of that. We do look after solubility. As I mentioned a while ago, most flavor compounds are oil soluble. Not all of them, some aren't, but most of them are oil soluble. And so we can devise extraction systems. And you'll see a couple of those in the lab as well. We'll talk about here. Stir-motor sodium extraction or solid phase microextraction. So again, looking for adsorbents, looking for basically ways to take advantage of their chemical properties. In terms of volatility, so let's say we were going to try to take advantage of volatility, we have to keep in mind what are the factors that determine whether or not a flavor compound is going to go into the headspace. Will that be released one way or another so it can be sampled? And this is a static condition. So you'll see that out in the lab. You put it in, you food, you let it come to equilibrium, and sample the headspace. That's not very sensitive, as you'll see later on. And so we've got ways where we try to take advantage of the fact that not much goes in here. Let's go ahead and try to do something a little more efficient. And so we can have a food sample down here, add an inert gas, helium, certainly nice gas with this nitrogen's okay. Pass it down here and then go off and pass it through an adsorbent. An adsorbent is going to absorb your flavor compounds into this tract. And so it's more or less coming across, we're sweeping the surface. A little more efficient, and then we call it purge and trapping. So we put purge, we put our gas and bubbles down into here. So we're kind of stripping the aroma out into the headspace and going into the adsorbent. We'll see each of these. We'll talk about it in more detail. But volatility different ways. But in all cases, we've got to get those compounds out of the food and into a gas stream one way or another. And the idea of volatility, it isn't volatility of the aroma compound that's so important. It is the volatility of the aroma compound in a food system. I mean, one thing is to have a pure compound sitting here. It can be very volatile. Take that compound, put it into food, let it dissolve in the fat, let it bind onto the protein. It's not so volatile anymore. So it isn't just volatility of the compound. It's volatility of the compound in the system that you're trying to extract out of it. And so the idea of fat's a wonderful solvent. That keeps the flavor in the food, doesn't let it go out into the environment. Carbohydrate, protein binding, and again, emulsifiers. We find a number of ways in which these compounds will react with the food. We got some equations that come up that kind of get the idea across. We probably won't go into them in a great deal of detail. We can calculate many of these things, many of the parameters that we want to know, but not all of them. And this is just partition coefficient between the gas to the food. So where is the volatile compound going to go? Is it going to go into the gas and raw food, or is it going to stay in the food? So it's the ratio of concentration of a compound in the gas phase divided by the concentration in the food phase. And that would be nice and simple if all of our foods were water. But that doesn't get us too far nutritionally or anywhere else. Supposing we put some sugar in that water, well, it changes the polarity of that solution. It changes the desire of these aroma compounds to stay in that water, that aqueous solution. Supposing the fat in there, oh man, there are those flavor compounds. They want to go right in the fat. They're not going to go anywhere. They're not going to partition into the water. They're not going to go into the headspace. And so this is really nice, looks really good, but it doesn't apply to us unless we're looking, like you say, at a dietetic beverage, perhaps. But every other food product, forget it. It just isn't so simple. So the idea of problematic, that has a high solubility in the continuous phase, or low vapor pressure, so it's not volatile, it's really, really soluble. And if there is a dispersed phase in there, like oil, that's a problem. So it's basically what I said. If it ends up being soluble in the continuous phase, the food is going to be a problem. If there's fat in that food, it's really a problem as well. And so if we just say, let's not consider partitioning between just the headspace, the gas phase, and water. Let's put a little bit of lipids in there. Let's make an emulsion out of there. How many foods contain fat? Well, a lot of foods contain fat. So if all of a sudden our concentration in the gas phase, or the partition coefficient between the gas and the food, starts getting more complicated. And so at that point, we have to start looking at the concentration in continuous phase and have to say how much of this food is fat. The more fat there is, the more it's going to swallow our flavor, and the less it's going to be released. So we start getting equations now that start getting a little more complicated. So partition between the gas continuous phase absorption into the lipids. And you can work through that and take a look at it. It does make sense. And so, obviously, you're not going to do this, but it's possible to go ahead and do some calculations on this. If that's simply a water and fat phase, if it's not just water and fat, which they never are, okay, then life gets more complicated again. And so we can actually approach methodologies. I have a philosophy that you start off as simple as you can. Don't make life more difficult. Let's start off the simplest methodology, then make life more difficult if it doesn't work. And so oftentimes, unless we have some prior knowledge, we do like to look at a static headspace. We do like to put the system into a closed vessel and just go ahead and let it sit for 1 hour, 40 degrees centigrade, 50 degrees centigrade, whatever, and go ahead and sample that headspace, and hopefully it's partitioned in. But sensitivity is always then an issue. So problematic. And also quantification gets to be a little difficult because oftentimes we're not so interested in what's in the headspace. We're more interested in what's in the food of these aroma chemicals. So we may want to quantify what's in the food. And how do you go then from what's in the food to what's released? So a quantification measurement in the food is not easy because of the previous equation set that we see. And this, whoops, if I can stop here someplace. If we do sampling, and so let's say we have our vessel, we've allowed it to come to equilibrium, we drop some sample. How much do we drop? Do we drop 1 ml of air, 1 ml of headspace, and put it into a gas chromatograph or a mass spectrometer? Do we do 10 mils, 100 mils, a liter, 10 liters, 100 liters, cubic meter? Well, okay. Tell you honestly, we're not going to go much above 1 mil. That's about all the gas chromatograph or mass spectrometer likes. You're messing with its system, you're messing with the carrier gas, the mobile phase. And so we tend to find ourselves someplace 1, 2 mils. We don't, in terms of headspace methodologies, we really don't get into larger volumes. And then we have to have a concentration at least of 10 to the minus 50 times 10 to the minus 6 grams per liter of an analyte. So let's say our aroma compound has to be at least in this concentration range to be able to detect it. And that's a bucket. That's a lot of material when it comes right down to it. So again, by headspace, if we could put a lot more in, yes, we could greater sensitivity. But we are stuck only measuring the most abundant things. When we did a PhD student from Land O'Lakes did a study on Parmesan cheese, and he wanted to have a nice complete aroma profile of that cheese. So he did do headspace, but then he also did two other methodologies. So we had rather three complete methodologies. Headspace to look at the most volatile, dynamic headspace to look at less volatile, and solvent extraction to look at the really non-volatile. And so headspace, like I say, has its place, but it's only for the most volatile components. So we work on in one way or another to concentrate that headspace. That's another approach. Let's get the headspace and let's concentrate it. And there's different ways we can concentrate that. Most of the time, we're going to bubble a gas through our sample or purge the surface of our sample, bubble it through. And that gas that you're purging through will contain some of your aroma compounds. And so you pass it through an adsorbent. And that would be a purge and trap. So we would purge our sample and try and trap everything that comes out of that purge gas. But there's also other approaches, ITEX, dynamic headspace. And again, we'll take a look at these in a little bit. And so in this case, we're not as concerned with the equilibrium concentration. We're interested in how well we purge a gas and remove, how well that purge gas is bubbling through your sample. How well will that be recovered? How well will that take out aroma compounds? And so we're really interested with the rate at which volatiles are released into a gas stream. So one is equilibrium, one is a dynamic situation. What will move into this flowing gas stream? Then, of course, the math gets even a little bit more complicated. And there's a really good publication. This is an old publication, but facts are still the same. And there hasn't been much better treatment of it than that. This starts getting into the rate of mass transfer. What's the rate of mass transfer of an aroma compound out of a food into a purging gas? Gas that's bubbling through your sample. And I won't bother to go through that. But you can take a look. There's a couple equations, and it lists each of the parameters, and hopefully you kind of look at that and say, yeah, okay, that kind of makes sense. Give it a try and see where you get. So the idea of purging, though, of bubbling a gas through a food sample, that's what we're going to do, and then trapping it is a nice idea, but it tends to get complicated. Anybody that's working with proteins, you start thinking about the really surface active agents. Gosh, they form great foams. And so I want to be bubbling a gas through this solution. And I want nice fine bubbles and lots of them. And then what happens is they foam. And so your tube, your vessel, whatever, fills up with foam. And eventually that goes through your system. You're trying to trap volatiles, and you have an absolute ugly mess. You don't have nice pure aroma compounds being trapped in a trap. You have water, proteins, all kinds of junk moving through these tubes. And so the idea of doing a good job of purging a sample and trapping the volatiles getting out that way is really a problem, because small bubbles, large surface area, and we end up getting foaming taking place. So it tends to work. It can be done in different ways, but it's a problem to do purging of food systems. And the most efficient purging are really tiny droplets of air. So lots of surface area of droplets, rising through your food product. Obviously, this doesn't work with a solid, right? You would have to, if you were doing protein bars, you take the protein bar, grind it up in water, then you'd purge inert gas through it and let that inert gas go through a trap to collect your aroma compounds. One of the problems with this, though, so we're going to go ahead and purge. We're going to hopefully get our compounds into that gas. We can trap them. But there is a problem. Aroma components seldom up totally. All aroma compounds in the food seldom are present at concentrations greater than 300 parts per million. You can typically flavor food with 100 parts per million of flavorants. But let's say we have a little bit of leeway. We'll say, oh heck, let's say we'll get up to 300 parts per million of flavor in this food. Well, what's moisture content? Typically 2% or more. Is moisture volatile? So what's our most abundant volatile in our food? Water. So what goes in the purge gas? Water. It overwhelms the system. And so that's just another complicating methodology, is that of the volatiles that we actually trap and collect, water's the most abundant. And we can't inject water into our gas chromatograph or into our mass spectrometer. And so we have to put another means somehow of kind of preferentially letting that water get through, but trapping our aroma compounds. And so how do we do some of these things? What are some alternatives? Headspace, purge and trap. It's purging. Nice idea. Works in some cases. But again, some cases it doesn't. It's like I say, we get a lot of water coming out. We get foaming occurring. And so we have a problem. So there's been some methodologies. So that's volatility. What can I do about solubility? Where do these aroma compounds want to go? Well, we can do an extraction. We could do a solvent extraction. We'll talk about that. You'll see some of those methods. But we've got a different methodology that's called stir bar sorbent extraction, SBSE. It's a stir bar. And that's a nice little tiny stir bar that's coated with an adsorbent. So it's a magnetic stir bar, right? It's coated with an adsorbent. So you put your food into a container. It's going to have to be a liquid. You toss your stir bar in there, and that sits and stirs all the while. It has an adsorbent on the outside that flavors tend to like. And so your flavors tend to be absorbed into that stir bar surface, that coating. And so what you can do then is go ahead and put that stir bar in for a certain amount of time, pull the stir bar out, rinse off the lumps, whether it's protein or nuts, whatever you happen to be grinding up or whatever you're studying. Just rinse it off quickly and put it into an instrument. Bring it up to 200 degrees. That'll strip off these aroma compounds and go into a gas chromatograph. Yara can tell you all kinds of stories about stir bar extraction, particularly the problems with it. She's shaking her head, yes, like, okay. Nice methodology that works in some cases, but in many other cases it just doesn't work. But as I said, most aroma compounds are lipophilic. You put a hydrophobic coating on that, and at least you've got a principle to take advantage of. So that brings us back, remember, to log P. The more positive the log P is, the more hydrophobic a chemical is. The smaller the log P, log of the partition coefficient, the more water soluble. And you look at many of your flavor compounds, as I said, they tend to be hydrophobic. And so they have log P's that are on the hydrophobic side. And they're going to like that adsorbent. They're really going to like that adsorbent on the surface stir bar. But some of them aren't. Some of them don't want to be on that at all. So it's not the answer to everything. Some things look good. Some things will be covered good. But other things won't be. In terms of solvent extraction, we'll have, I guess, only two methods of solvent extraction in the lab tonight. But certainly, you can go ahead and take just a separatory funnel. You can take your food, put it in a separatory funnel. Again, you make an aqueous blend of it, solution of it. And go ahead and put a solvent in there. So you dissolve your food in water. Put an organic solvent, shake the heck out of it in a regular separatory funnel, let them separate. Your flavors will tend to move into that organic phase. Of course, if it didn't form an impossible emulsion in the process, which it oftentimes does. And so this is the fraction that's extracted in the process. Here's the volume of water. Here's the oil-water partition coefficient times the volume of the oil phase or your food phase, plus the volume of water. And so if we simply take two compounds, just to illustrate, we take diacetyl and I take eugenol, and we put them in water. We put the water with those two compounds in a separatory funnel, put our solvent in, shake them up. What's the partition? Where does our flavor go? Does it go into the solvent like we want? Because when we take that solvent, we're going to concentrate and do our analysis. And so we really want to get our flavors out of water and put them in a very volatile solvent. And so if we go ahead and do this extraction, and just an example, 100 mils of organic solvent should have about the same amount. Oh, okay, 1 liter. Here we go. 1 liter of water, 100 mils of organic solid for extraction. If you go through this extraction, you're going to leave 99.5% of the diacetyl in the aqueous phase. So you only extracted 0.5% of the butter flakes out of this process. If you look at the eugenol, only 4.1% remains. So we extracted almost 96% of the eugenol and only 0.5% of the diacetyl. Does that represent our mixture? Our mixture was equal parts of both of these, but what we extract with a single extraction is really biased. We find an awful lot of eugenol in our extract and very little of our diacetyl. And so what do we do? Well, what we try to do is more extractions, right? Instead of doing one batch of 100 mils, you divide it into maybe 20 mils each time. So use 20 mils of solvent. And so we put 1 liter of your flavored water or beverage, or whatever we want to look at for a study. We put our liter into the separatory funnel, add 20 mils of our extracting solvent, that could be ether, dichloromethane, two very volatile materials that permit us to evaporate and concentrate. And do it this 5 times instead. So extract 20 mils of pure, clean organic solvent, collect that, 20 mils again, shake, extract again. So at that point, we've extracted 99.9% of eugenol into our organic solvent, but we still have left by far the vast majority of diacetyl. And so it's a problem where we've extracted almost none of the diacetyl, no matter how much we shake it. It's not soluble. And so if you were thinking you want to take a food product and you want to determine what's the flavor profile, what's an off flavor, what makes it taste good, and you do an organic solvent with extraction, what are you going to see? You're going to see those components that like want to be an organic solvent. It doesn't represent what's in the food itself. So I guess I'm going through some of the challenges. How's that? And this is certainly one of the problems with organic extractions. Polar solvent, yes, we could use a slightly more polar solvent, but we can't go very far. Polar solvent would have got more diacetyl. So we make a choice. We could extract with pentane, or we could extract with diethyl ether. If we extract with pentane, we'd actually extract no diacetyl, extremely nonpolar. If we use diethyl ether, we get a little more of our diacetyl, but still not much. And so the idea we can change polarity of solids a little bit, but not enough to get us very far here. So organic solvents are always going to give us a really biased picture of what truly is in the food product. So large bias in sample recovery is kind of the story. What you see isn't what's there. And so this would be, let's say we go ahead and we decide we like that kind of stir-bar idea. That was kind of cute. Let's take this little stir-bar, let's put in that sorbent on it and drop it into our food and let it stir in there for a while. So that's the SBSE, the stir-bar that's coated. You probably have come across SPME. That's mentioned in food analysis as an extraction methodology. That's a little different system. For a stir bar, you've got this little stir bar with a good deal of this coating on it. For SPME, solid phase microextraction, this material is a very, very thin coat on the needle. And that needle gets pulled up into a sheath, so it's protected. Then you put it down into your sample, and you push the plunger down. And now this adsorbent, this very thin coat on the needle, is there so that any kind of aroma compounds that like it can be attracted to it. It can be in the headspace to attract aroma compounds out of the air, or it should be immersed in the food and have flavor compounds move onto the stir bar. And then this is a little bit of math along those lines. Again, you could spend time with it, and I'm sure you'd certainly understand it. The one thing I want to point out about these two methodologies, SPME and stir bar, is that they differ a great deal in their ability to extract flavorings. And roughly 80% of the work that's published in the flavor area is done with SPME. Only 20% gets divided up to other methodologies. And SPME is a horrible method. It comes right down to it. It's a horrible method because it has a very, very thin coating on that needle. And that coating is very selective. And so it doesn't extract a great deal. So it troubles me. I review articles that are very common. And every time I see SPME, I cringe because of what they didn't see. But it's convenient. It's easy. We take the needle, we push it down, we let it sit for 20 minutes, we take it out, and we get some result. Horrible result. Not a representative all, but we get some result. The stir bar has a much thicker coating. That's the next slide. Probably the next one. Much thicker coating. So we get a much more representative sampling. So I'm okay with the stir bar, but I'm not okay with SPME as a methodology. And again, this is more than we need to do to go through the math on it. This is a paper that's published in one of the GC journals, the gas chromatographic journals, and it was comparing the recovery of aroma compounds using the two methodologies. And it looked at the recovery of aroma compounds depending upon how nonpolar they are. And this is the SPME. And so we look down here, it has any water soluble. Now this is starting to get a little bit nonpolar, quite nonpolar, really nonpolar, very, very poor extraction. It's only the real extreme nonpolar compounds that SPME attract. Stir bar is much more sensitive. It's not good if it's not water soluble. I'm sorry, if it's not oil soluble. But it only has to have a little bit of hydrophobicity before you start seeing compounds. So stir bar is vastly superior to the SPME methodologies. And like I say, when you see 80% of the work done on that, that's not good. And there's example concentrations. Again, we could spend another 15 minutes to go through the math. But these are the two chromatograms that kind of show you exactly the same sample analyzed by the two different methodologies. If you use SPME, you'll see some compounds out in here. This is retention time, so this is your chromatogram. And so kind of go along from here. And you don't see much at all early because these tend to be a little more polar compounds. They tend to be very volatile compounds that come off first after your gas chromatograph, and they largely aren't seen in your sample. Here, you're getting a much more complete profile using a stir bar methodology. So there is a paper that it is absolutely a must read. Every time I review a paper that used the SPME, I also, in my comments, you might want to read this review. It's a very thoughtful review from Dijon, France, from INRA. And really a nice review that talks about SPME and the weaknesses of it and how to use it properly. So that we spent quite a bit of time with a couple methodologies because they're so broadly used. Headspace is used, SPAME is used a great deal. Like I say, really, really weak methodologies. And so what we're going to spend the rest of our time tonight is going through other approaches. And so I've mentioned headspace, but I'll say a little bit more about headspace concentration. We'll take a look at some distillation methodologies, some solvent extraction, direct sampling, and of course our SPME or SDE to a much lesser extent. Headspace is redundant. You got to measure what's in the headspace above a food. And so that really depends upon the food composition. So what's the food composition? What are compounds of interest? And of course, what drives things into the headspace? Temperature. Can we tolerate heating the sample? If it can warm the sample, we can certainly drive flavor compounds into the gas phase. But how much can we heat them before we start forming artifacts? As I said, when we talk about it, we're talking about only the most abundant compounds we're going to see. And so that really depends upon the food and the compounds we're looking at. So dynamic headspace, I think we got a diagram of two different types of dynamic headspaces. This is at one time McDonald's had the greatest French fries in the world. I don't know if they still do. But okay, this was a device for looking at French fry flavor. How's that? And so this is a rather large jacketed vessel. It's open in the center. This was filled with French fries. How's that? Blown up French fries. We got an inert gas here, and so we're putting inert gas here. So any vapors, any aroma compounds given off by the French fries move into this gas. Then this is just a cold water trap here, and the liquid nitrogen traps over here. So anything comes out is going to be collected in one of these flasks. And of course, the most abundant thing you're going to collect is water. So then you still have all your aroma compounds and water in one way or another to get them out. This is an automated approach to that. And so if you kind of look at this system, so in this case, you've got a gas coming in, it goes through a valve, and comes through, it gets, this is just a tube, so it might be a tube about that big around, about that long. And you have some of your liquid in here. Could be beverage, could be a protein bar, whatever, busted up in here, in water. And so your gas comes through here, it bubbles out. It's here, and then goes back in this direction into a trap, mid-sorbent. And the trap is very good at picking up hydrophobic compounds. It's a granular material, so granular packing that loves hydrophobic compounds, and then comes out, gets vented. So this trap supposedly collects everything that's going into the gas across here. And because it likes hydrophobic compounds, all that water doesn't tend to get caught in that trap. So it's a way of separating your aroma compounds from your sample and from the water. And this switches into the real trappings analysis cycle. Now your gas chromatographic carrier gas comes through. It goes through the trap, which is now heated, and goes into a gas chromatograph. So in one case, you're passing whatever is purged here to the trap. Now you desorb what was trapped here by heating going into a gas chromatograph. Like I say, what is commonly the problem with this is it forms an emulsion, foam, I guess I have to say. So it forms a foam, and more often than you'd like to remember, that foam starts coming out from here, then it comes from here, comes from here, comes from here, down here, out there. Looks like a rabid dog from foaming at the mouth, frothing at the exit point. And it's ugly. It's almost impossible to clean up. And so again, your problems always are with this. What do you do about foaming? Because the finer the bubbles that you can get here, the more efficient, but then also the better foam that forms. A different way to do this kind of trapping system, this is called ITEX. And so in this case, you've got a syringe, and on that syringe, you have an absorbent material. So you can pass gas, just like through this purging system, we have a trap. So this is filled with a granular adsorbent here. You put this down into your food sample, so this is the headspace above a food sample, and you can then draw some gas through that trap and vent it, then draw it again through the trap. Each time you get some aroma compound. So basically you sit there pushing it up and down, and that tends to take the aroma compound from here and put some on the trap. Just another way to take that headspace and put it onto a trapping system. This is kind of comparing the same sample by doing isolation by 3 different techniques. This is the chromatogram bit by headspace. Not very interesting. In fact, there's actually nothing visible. How's that? So you just directly checked it. You see nothing. If you do the ITEX, so you're going to keep moving this plunger, sucking that headspace of the sample in and out over the trap, you see something. And here's a solid phase micro extraction, and then there's dynamic headspace in there. And by far you get more from the dynamic headspace of Hershey trap systems than you do from the other methodologies. The pros and cons. One of the promises is a single use, a single extraction. You get an extract onto that adsorbent, you desorb it into your instrument, and you don't have a second chance. You got to start all over again and go through another whole trapping process. And so I say it's single use. I may want to have trapped my aroma to let you smell it. So, it's at the end of a gas chromatograph and smell, and you should smell it too, and you should smell it too. And then we should do mass spectrometry, and we need gas chromatography. I'd like to have about 6 or 7 chances at this, and every time I want one of those, I got to go through this whole darn process again, because it's a one-shot deal. Water-soluble materials, fermium, maltol, vanillin, you're not going to see them. They love being in water. They're water-soluble components. You'll see just simply the more hydrophobic components. It is fairly precise. It's pretty reproducible. Few artifacts. It's simple. But again, it has a number of weaknesses in terms of sensitivity in that. I don't think we set up any batch extraction because I assume every one of you are familiar with the separatory funnel. If you're not, you should. But again, this is something you do. Maybe interested in something, the aroma compounds that happen to be in a beverage. And so you could put the beverage in here, put your organic solvents in here, shake the heck out of it, drain them off, and collect the organic phase concentrate to do gas chromatography. So that's really not too efficient. You're more efficient if you can do some continuous extractions. And so this is a continuous extractor for systems where they use a solvent that's lighter than water. So diethyl ether, hexane, pentane, good solvents. In that case, you put your, let's say diethyl ether, I like ether. Let's put your ether over on this side. We'll start heating that ether. We put your food over here, whatever you want to extract, on this side. So this is filled with your sample you want to extract. So you start heating this, the ether vapors come up, they get condensed here, and this is a tube that goes all the way to the bottom, the little bubble around. And so the ether drops into here, builds up some kind of a head, and eventually it pushes the ether out, and the ether comes bubbling up and drops back in here. So this is a constant reflux, always extracting with distilled solvent. This solvent is distilled, so it's a distilled solvent, always extracted here. If you want to use a solvent that's heavier than water for an extraction, so we can both set up in the lab, here you can have dichloromethane. Dichloromethane is one of my favorite solvents too, but it's heavier than water. And so, again, you heat this solvent over here, dichloromethane vapors come up here, they will condense And here's your food. So your food is up here, the liquid or whatever you want to extract. And so this keeps on dropping through here, building up ahead and running down through here. At this point, we've got dichloromethane again, and so it comes down here, and is how it's reflux. So fairly simple continuous extraction systems that really end up being quite efficient. Some of our most common solvents, like I say, diethyl ether, dichloromethane, pentane. You want a solvent that's very, very volatile, because in the end you're going to end up with maybe 100 mils, 200 mils of organic solvent. What do you do with that? You have to concentrate your aroma compounds, which means you got to evaporate some of that solvent away. If it has a high boiling point, as you're evaporating the solvent, you evaporate your flavor compounds, so you have nothing left to measure. But if you have a very volatile solvent, like one of these, you can evaporate that down and maybe take that 100 mils of solvent down to 0.1 mils and still have your flavor compounds left in that solvent extract. Good efficiency. You can run these things around 1 hour, 2 hours, 4 hours. So it's good efficiency, low cost. You have problems again if your food forms an emulsion. Forms the emulsion, you drop your solvent in there one way or another, and all it does is form bubbles of solvent in your solution. And it's tedious, it takes time. Your solvent has to be really clean. And so dichloromethane is really clean solvent. Ether isn't. So if you want to use ether, then you got to distill your ether. And if you know something about ether, it forms peroxides, which become explosive after some time of neglect. How's that? It doesn't happen quickly, but did we have a bomb squad come into one of the labs? Was that for ether?
Yeah.
Yeah. If you're if you're in the business of working with ether or working with organic solvents, and you happen to open up a cabinet and you find something that's ether that says 5 years old, 10 years old, you shut the door and you call the bomb squads, just because it's explosive. And so they have to be handled really carefully. So I like ether, but I like dichloromethane because it doesn't have a problem. But you do have a lot of organic solvent, and most of the time in our lab, we evaporate them under a gentle stream of nitrogen. So you may have 100 mils, you have a gentle stream of nitrogen, a little heat, and you just carefully evaporate off the majority of the organic solvent. There are more complicated ways to do that fractional distillation, which we do sometimes, other methodologies. But you always then end up having to concentrate your sample extract. Supercritical CO2, that's really good solvent too. Works really well. Has some advantages in that as soon as you release the pressure, your CO2 evaporates and you're left with your flavor molecules. So it's actually good solvent. So it's a good solvent for extraction. There's an advantage, it's so easy to concentrate in the end. The problem, of course, is you're dealing with something under high pressure. And so it requires a really good high-pressure extraction system and controls of it. And so it doesn't tend to be used much simply because of the cost of the apparatus. It doesn't offer enough advantages that it tends to be used. And one of my favorites methods, you'll see quite a variety of different ways that you can go about this whole process. But it is a challenge, I'm going to say, to get the aroma compounds isolated out of food. So this is what you're going to see down the lab too. It's called the Likens-Nickerson, and that was actually developed for beer flavor. And so what you do is you put your flask of beer, round bottom flask of beer down here, you put it in heating mantle, and you start most stable beer. You start, we put it over on this side. There we go. So we put our beer over on this side, and we start evaporating, so we've got steam coming off this. The steam comes up this side. On the other side, we've got our diethyl ether, so we've got ether being heated here. So you have ether vapors coming up here. We have beer vapors coming up here. They mix, they condense, and they will drop down here. Now, water is heavier than ether, so the water drops down here, collects and runs back into the beer trap. The ether is lighter, so it tends to stay on top and comes back here. So you've got a continuous, so I should go that way. A continuous extraction going on by distillation. It is really a good method for extracting medium to high boilers. If you have something that's really volatile, you do have to evaporate that solvent again, and you can lose many of your aroma compounds. So it's really good for medium to high boilers. It gives us a lot of extract. A lot of extract that I can use many times to inject it and smell it and do all these other things. Problems we have is you might want to use an amifoam because maybe that foams. Oh, now you got artifacts coming from the artifact foam. If you would run this under a vacuum, it can be run under a vacuum. We've got vacuum grease as a contaminant. We have any contaminants from the water, from the solvent, from any tubing that's involved to hold the vacuum. Thermally induced artifacts, and so I'm talking about all the possible artifacts. And yet it's, like I say, a fairly common methodology and a fairly good methodology. It's this gives a view of some of these methodologies. So this is a mixture of aroma compounds. It's ethanol, propanol, butanol, octanol, decanol, ethylpropane, ethylbutyrate, ethylvalerate, ethylcanoate, not acetaldehyde, something else like that. But methyl salicylate, carbone, if we kind of go across through methyl, travel, butanol. So a bunch of aroma compounds. And they should all be up here at 100%. They've all been put in at a similar level. And so they've been put into water, all the same concentrations, and perfect extraction we have a line right across 100%. If this is put in a separatory funnel and you extract from the separatory funnel, this is what your profile looks like. You've completely lost some of these compounds. You retain a little more of these as they get more and more nonpolar, but then these don't have very good boiling points to lose them. And so batch extraction of pentane gives you that profile. This is probably one of the better profiles with dichloromethane extract, still missing these small molecules. This is solid phase, or the steam distillation method we just saw under vacuum or under atmospheric pressure. But the take home here is none of these methods give you all the compounds. Every method has a bias. This misses the early ones. This misses some of the early ones. Certainly doesn't do justice on the higher boiling compounds as well. So every method is a compromise. Whenever we do an extraction, so we end up with some kind of an extract, what do you do with it? These things are highly concentrated. They will evaporate. It's always, I was going to say amusing. It's not amusing. Interesting, maybe that's a better word to put it. But you may get an extract, and you've worked at it for a couple of days to get this nice little extract. You put it in a vial, it's got a Teflon cap, you close the vial down, you put it in the freezer, and 3 days later it's gone. And then you start all over again because it evaporated, was absorbed, it escaped one way or another. And so what you could do is you put your collected fractions of liquid nitrogen, CO2. Some people even put an antioxidant because these aroma compounds can oxidize. They're in the air. They will oxidize. So it's interesting. You get an isolate. How do you preserve that isolate? This is what you're going to be showing a safe extract. So this is the methodology that actually 3 of you are using. So this is the most common methodology that we're using in the laboratory. And so Yara will go through this for us. So just quickly, Yara will have done some kind of a solvent extraction of our sample. So it could be ether extraction, dichloromethane extraction. And so this will be dripped into a high vacuum. We've got a high oil infusion pump, turbo pump over there. We're talking about high vacuum whole system. And so this is going to be dropping in here. and it flash evaporates. And the idea is that solvent carries your raw compounds with it. They condense here and will be caught in the cold flask down here, liquid nitrogen. Any ones that want to really escape and go out with the pumps get caught again by the liquid nitrogen traps. So it's a way to put a sample in here. She might have done an oil extraction of, fish, and you could be talking about pennycress. You do a solvent extraction of pennycress. You have oil in there. You're doing enzyme modified cheeses. You got butter fat in your oil sample. You're working on pea flour. You've got oil in your samples. So this is a way. You've got oil and solvent here. The oil is up here. Your oil compounds end up over here. Extremely tedious. It's tough to do an extract in what, 1 day about for how much? 2 days. 2 days per sample. It gives you a nice overview of compounds in a food. Tedious. It takes a great deal of time to, 2 days per one sample. That's not an efficient way to do it. So here's just a couple of other methods that I've talked about already. This gives an example of the solid phase microextraction. So this is like a syringe, but that syringe is a long plunger that actually can be extended out here. And this is where the absorbance is. There's an absorbent on this. So you can pull it back so it's protected and put it into a flask through a septum or anything like that, and then expose the fiber. So it's fairly simple methodology, and that's why people like it so much. You can go ahead and cut it. Here's maybe your sample. Get your sample down. You can actually put it in the headspace. You can put it into the material itself. After so many minutes, so it's 15 minutes, 30 minutes, 2 minutes, whatever, you've gotten some normal compounds absorbed. You put this into your gas chromatograph, mass spectrometer. This ejection port of your GC, gas chromatograph or mass spectrometer. That's 200 degrees centigrade. You have your gas coming in here, sweeps your sample into the column. So very, very simple, attractive, and that's what people say. We use this methodology because it's simple, it works. Well, they don't say it works well. They say everybody else uses it. That's their justification. So everybody else is doing it wrong, so we should do it wrong. I'm a little more polite in the review, but it troubles me that people don't think about it. Reproducibility of fibers, these needle coatings, they differ from one to another. If you're doing a shelf life study and you start off with one and it breaks, damage, it deteriorates, then you got a different fiber, you have different results. And so what happened to your shelf life study? It is a competitive process. There's not much coating on that needle. So if you put it in for 1 minute, things are going to go for it. You put it in for 5 minutes, you're going to start getting competition. Wait a minute, I like that better than you. You go away, you start displacing things, and your profile changes because of equilibrium is tending to occur. And so that gives you certainly a problem. Lack of capacity, you just don't get much sample out. So again, whenever people publish with this methodology, they talk about all the wonders of it, how good it is, but they never bother to go with the shortcomings. Many other choices, and it's interesting that when you read the literature, there's some very large groups. Some groups maybe have 20, 30 people working in them, and everybody has a favorite method. And so if you had 20, 30 people working in a group, and they have a favorite method, they all use that method, you see them showing up a lot in the literature. And if you're reading literature, you say, oh, everybody's using this method, I should too. And that's, you shouldn't go that direction. You really need to think about the methodology. There are many different choices. And what's most abundant in the literature isn't necessarily the right one to go for. And the idea, no one method's going to give you a good profile, let's say a complete profile. And so you have to keep in mind that you may want to use 1, 2, 3 different methods to try and get a decent profile. That, again, is extremely tedious. Strongly depend upon the goals of analysis and keep it simple. Well, we'll come back to this Yeah, let's take a 10-minute break and then come back. So anyway, let's. I think that pretty much said what I wanted to about aroma analysis. It's certainly not a simple task to go about trying to get the compounds and get a representative sample. And there's, like many things in life, there's no perfect way to do it. And every time you pick a methodology, it's a compromise. You're going to see some things, you're going to favor seeing some things, and you're going to miss other things. And you have to keep that in mind whenever you're doing these things. It may be the right approach, and it may not. So anyway, we'll move on. We won't spend a great deal of time with taste analysis. And then I think if we have some time, we'll just start something on emulsions, because I sent emulsion slides to you before. So let's do taste analysis. It's kind of interesting that really taste analysis is simpler in some ways, and it's more difficult in other ways than aroma analysis. It's simpler in terms of the extraction procedures, the processes that are used to get taste compounds out, and for that matter, to separate them. But it ends up being more of a problem in identification. And so, in our case, our problem is getting the darn aroma compounds out. We've got wonderful libraries, which still doesn't make it easy, but for mass spectrometry, we've got a lot of information, mass spectral data. So it really helps us in identifying what we finally extract. Still not an easy challenge, but when we get to taste, it's really simple extraction and a tough identification. So there's just reverse in where the challenges come. The greatest challenges in taste come in identification.
Ask a clarifying question when you say taste. Because I know, like in the sensory center, we have like a very strict definition of like flavor, taste, and aroma.
Yeah. For me, it's all
just your body taste.
Yeah. We don't put anything else in there. I really don't like kukumi. I don't know how you feel about kukumi, but anyway, no. Okay. Why is this simpler? I think because the rules are generally applicable, that taste compounds are water soluble. There's exceptions to that. Acetic acid is water soluble, but not the other compounds have very limited water solubility, but enough. But in general, we assume they're going to be water soluble enough that you can extract them from the water and do your analysis. And so we kind of make that assumption. So we're not looking at organic solvents. If the idea that more complicated it becomes in terms of identification, and much larger molecules, more complex molecules, things that are poorly described in the literature. So they say we kind of assume that these things are water soluble, so our methodologies work for that. They can be volatile, but in general they're not particularly volatile. So different rules apply. In terms of, like I say, the challenge, we don't have the LCMS. So we're going to do liquid chromatography, not gas chromatography. And we're going to use mass spectrometry very heavily for follow these compounds, monitoring them and identifying. Some of the solvents that tend to be used then could be water, methanol, ethanol, formic acid, water. We'll tend to stay with a limited number. If oftentimes the pathway we're going to go down, we're going to do some isolation, fractionation, we're going to be tasting. Okay, we don't like to be tasting formic acid. Methanol is one of our better solvents for tasting it again as well. Formic acid, no. So anyway, if you're going to be doing tasting of them, then you typically limit yourself to water and ethanol. Nobody complains about ethanol. It seems to actually make things go a little better. And so what you start off with is the assumption, okay, they're water soluble. Now, in some cases, you can actually run the sample through it in HPLC. So do liquid chromatography on a food sample. If it's a liquid, that's probably what you go ahead and start with. However, oftentimes you need to do some fractionation of that. And so you need to use gel permeation chromatography. Do an extraction, use gel permeation or membranes. And very commonly, you limit yourself to about 2,000 molecular weight. So you can take a food product and use membranes and take only things 2,000 molecular weight or less. So it passes through that membrane. And so you'll use that as a beginning material that gives you a crude fraction, which then you do use that one for then LC analysis. So you may start off very commonly, you just start off with a gross fractionation, 2,000 Daltons or less, and then do HPLC fractionation. You typically are going to be using two-dimensional LC, so you use a polar column, you use a non-polar column, so two-dimension separation. We don't tend to make derivatives. That was in one of the papers, so people were actually making a derivative. So they will get a fraction off the LC. They maybe can't identify it. They'll take and evaporate off the solvent, maybe make a derivative, a trimethylsilane derivative. And then they can do gas chromatography, mass spectrometry, which gives us a little better identification, sugars, organic acids, and so on. But your processes is, like I say, doing this initial fractionation and then HPLC analysis. The idea that we're going to then get an HPLC profile that comes off the LC, and you'll do fraction collection. So you just start collecting fractions. We want to collect 5 mil fractions, 10 mil fractions, whatever you're going to do. But you cut into fractions your eluent. And that at that point, then you start doing tasting. So you can taste those fractions. Now, needless to say, that column has never been used for anything other than tasting from it. And so you don't worry about necessarily anything coming off the column from some other analysis. But you have to be really careful if you have people tasting things. And I think that there's, what's IB? What's the regulation body that says you can't taste things without approval?
Oh, IRB.
IRB. I knew there was a B in there. Now, where did that come? Yeah, IRB approval. And so you get IRB approval for the methodology, for the solvents you use, and how you run the analysis. And then there's different ways that you come at that point. Most of the time, what's done is you will then taste these materials at different fractions and say, are they bitter? Are they sweet? Do they have umami? What kind of character do each of these fractions have? Again, use more than one person, and it's always the case. Use more than one person for tasting these materials. And the idea that you can collect fractions, and if you've got a preparative LC, you can get some fairly decent-sized fractions that more than one person can evaluate. I didn't get my act together. I should have put in the part about doing gas chromatography, olfactometry. I just kind of went through the analysis, the isolation. I should have also put the idea, well, so what? How do you decide which of all these peaks are important? That's going to have to come next time. Because that's exactly what we do here. We do fractionation, we get fractions, and we start having people taste them. In our case, with gas chromatography, we sit at the end of the instrument. As each compound comes off from the column, you smell it and say it's got an aroma, it doesn't have an aroma, it's intense, and so on. So this is really analogous to what we do by gas chromatography, collecting algulates or material that comes off of an analytical column for gas chromatography. We do the same thing here, collect the fractions. And very commonly, the fractions are adjusted in concentration. So you started with a certain amount of sample. You've gone through various isolation steps, and finally the fractions. How much does that fraction represent? Does it represent, 1 kilo of cheese or 100 grams of cheese? It's diluted to be about the same concentration that fraction would be in the food product. So you're tasting the product, multiple people, and you're tasting your isolates at the same concentration that they would be in the food. And you're hoping then that gives you an idea, because you could take many things and concentrate them enough they're going to have a taste. But so if you adjust them to the same concentration to be in a food, then you're at least dealing with things that would be relevant in that sense. And again, there's once you get fractions, you can combine them, you can adjust the strength of them. You can do all kinds of things, which you don't tend to be able to do with gas chromatography. And so by liquid chromatography, you've got more opportunity to combine fractions and look for interactions. And so you can also do addition of other materials, sugars, or whatever else. So there can be a lot done with these fractions. The people have come up with a taste dilution analysis, and this is kind of the same thing that we tend to do with gas chromatography and aroma. We started with a dilution analysis for aroma compounds. Let me go ahead and do something with that. So let's say, your gas chromatogram comes along here, you're sitting at the end of the gas chromatogram, you're describing the smell, maybe there's a smell, another one. So you may have all kinds of different peaks. And with the gas chromatograph and the aroma, which of these are important? Well, that's where the people come involved, that are smelling. But the idea that maybe you smell this and you describe it as cheesy. I suppose I could have said pennycrust like that. But this may be cheesy, this one may be smell like my dog, the other one smells like wonderful fruit. So as you go through this, you're just sitting there at the end of this column with, like I say, the column comes out of the gas chromatograph, and you say that you smell whatever comes off, and you describe each of them. But that still doesn't necessarily tell you what's important. They have an odor, and you might say they're important, but how are they important? And that's where we start getting in trouble. We're trying to put this back together and make some sense of it in terms of the food product itself. So there's been different methodologies that have been applied to these kinds of judgments. And one of them is a dilution analysis. And by that I mean, so let's say that we go ahead and we're extracting something. And now we'll click on that. We'll give equal time. So pennycrust. And so you can get this profile of pennycrust of aroma and analytical peaks. And how do you then determine what's important? Well, the way that it tends to be done, and it violates every rule of sensory science whatsoever, because this was developed by chemists. Chemists don't necessarily do sensory science. And so what people will do is they'll take their isolate, their aroma isolate, they'll do the gas chromatography, and they'll get all these different odors and so on, whatever. And then they'll dilute that sample. Maybe dilute 1 to 3. Let people smell it again. then maybe dilute it 1 to 3 again. And dilute it again. And they dilute it until there's no smells. And then they kind of add these up. And they say, oh, well, wait, we need one compound over here. This compound can be diluted the most and still smell. Therefore, it's the most important. That's where you should set it up in the chat, right? And so, so one compound can be diluted more than all the rest. That's the most important compound. The experience contribution, which doesn't make sense. And so they'll actually start ranking. Okay, that's number 1. Oh, maybe this compound. We'll say that's number 2, but it'll be based on dilution. What smells the most dilutions. That's called dilution analysis. And I've had all kinds of problems with the methodology, and I tend to disagree with people in meetings about this, but they simply leave it at that. The problem is we've got to have some way to judge these. We have to have some method of saying what's important, or we can put a focus on it. We don't have a good way to do it. We really don't have a good way to do this in real time and reasonable. And so this is kind of lived on, and it got transferred into the taste. And so the taste analysis is the same kind of thing. So you taste diluted samples. You have this fraction you collected from your LCMS. You dilute it and taste it, dilute it and taste it. Oh, okay. Again, the one I can dilute the most and taste the most must be most important in the ranked in that manner. And so this work comes largely from Thomas Hoffmann in Germany. He's now, I think, the head of research institute in not Berlin. He's the head of nature university at this point. And he has a group of probably 40 people working under him doing this type of methodology. And he says, okay, aroma extract dilution analysis, and it's used now for taste. So did it for aroma, which they developed also, and doing it for taste. And it's really a problem, because what troubles me is that if you kind of look at smell or sensitivity, there's a relationship between concentration and intensity. One compound would do something like that. Let me make this straight. Sorry. Might be longer than and so, one compound may have a very poor relationship between concentration and intensity. Another compound can be like this, another like this. So this compound may be present twice its threshold to knock your socks off. So it could be 100 times its threshold. It's still be gentle. Vanilla is a good example of that. People just, you can have more and more vanilla, more and more, and it never becomes offensive. Take something like purple mercaptan. It's in that category. And so the idea of using that methodology for taste, which I'd say is developed there, and then is here over here, just isn't logical, but that's what's used. And again, why is it used? Well, what do we do? Is kind of where we're at. If you've got, you just identified 100 different compounds in food, and you say, well, what's important? How do you do that? What you have to do is you have to do some really good sensory work. You might try to go ahead and, we try to do this with coffee, try to deodorize coffee. Just run it through a vacuum still, and have coffee that doesn't have any aroma. Then we can put an aroma compound in there at different concentrations and look at intensity or look at contribution. But that takes a good deal of effort, and we never got, by the way, deodorized coffee. We can never get rid of the odor of the coffee. There's things that have such a low sensory threshold. We would do that. We were working for Nestle.
Now there is another version of this one, and there are many versions. So one of them is charm.
Charm is the same as that. Yeah. It's from Terry Creek. And, and this is called aroma extract dilution analysis. There's another method called odor activity values. And what they do is they do it a little different. When you find a compound that has an odor, they quantify it. And so you can be parts per million, whatever you want. And then they look up in the literature for thresholds of compounds. And they say, oh, here's the threshold of methyl and and so find the threshold is 0.001 ppm. I've got 5 parts per million here. Look how much, what about the sensory threshold that is. That's 100 times the sensory threshold, 500 times the sensory threshold. Must be most important. So this one takes into account thresholds. But the sensory thresholds can be different by what? In relation to 100, 1,000 times. It depends on the food product. And so what threshold do you use? And who says that threshold is valid in this particular product? And what food was that threshold in? Was that food in eggs and you're going to apply it to coffee? Give me a break. So this is method. That was the next version. After this came under a great deal of criticism, this was the next approach by the chemist. And it still doesn't make any sense. It just still isn't valid by sensory improvements. So you'll find that we don't have a good methodology here. And
do you see data like this being mapped with statistics against discrete analysis data, comparing to see what sensory panel discrete analysis came up with, or to see about those compounds?
You mean, I'm sorry.
Yeah, so doing one of these kind of dilution or
analysis,
and then also doing a discrete analysis of set with some of these isolates as the reference using statistics to do
the chemists don't tend to do this. It's altogether too complicated, and it takes too much time and too many people. And then they generally train for it. They generally come out of chemistry laboratories rather than foods laboratory. They may do a food research facility, but they don't have that training. Anyway, so these are the approaches that tend to be used to try and determine what's important. And every one of them is flawed, but it always comes down to tell me something better, that can be done in a practical sense. And there just isn't a good alternative. You need to get back to finally individual compounds and ideally put into a deodorized matrix. It's the same matrix. Do combinations, are they important at that point? Can you smell them? Do they represent some of the characteristics? If you did some attribute profiling, there's just, they don't tend to go that direction. But everybody smiles and publishes it, and that's how it goes. How's that? So again, they've developed these types of approaches over there for aroma compounds. They gone ahead and developed similar systems for taste. We said, oh, it worked well for taste, so I'm for aroma. Let's go ahead and do it for taste. And like I say, it's just not that simple. And there's actually people doing a little more complicated things where they start putting things together, combinations together, and so you can find some nice systems that deliver blends together to two people and try to make some sense of combinations of aromas. And again, if you start going through the literature, these are just some examples of literature. Water extract of cheese, centrifuge remove the fat of larger insoluble. So you've got a fat layer on top, you've got some kind of a pellet or insoluble material at the bottom. Size fractionation, and then ultra nanofiltration. In this case, they didn't look for individual non-volatiles, but they just said, what's the important importance of taste compounds. So they got a fraction they considered that represented taste and put it together and said, does it taste like a cheese? So it could be in Gouda cheese, water extraction, centrifugation again, freeze drying, gel permeation, and then simply fractionation off gel permeation. Gel permeation doesn't have much resolution. It's not a very effective technique to separate compounds. That's pretty coarse. Again, different fractions coming off LC-MS, doing isolation again on a nonpolar column and on a polar column. So you start trying to fractionate individual fractions and see what components in that fraction might be causing the problem. Because again, it's really hard to get pure fractions out of LC, and you may do the two-dimensional. So you're going to take a fraction you collected once and try it on this column and do it on that column afterwards. But it's not a simple separation. Again, this was Kokumi. An omission sensory testing. I told you about the triangle test for strawberry. No, I don't see a lot of smiles and yes. Okay, so omission testing. Now that's always interesting because that's again what chemists think is important as a way to look for what makes a contribution to a flavor. And I was in a meeting where fellows had just identified 6 components that were absolutely essential to strawberry flavor. So 6 aroma chemicals. And he did omission testing. He left out one and said, triangle test, can you tell a difference? And he picked the most likely one, and once you know that made a difference, the sensory panel can tell a difference on omission. Then he went through a second one, yep, they can tell a difference. Third one. Finally, even the 6th one, 2 out of the 6 panelists made the right decision on choosing the right sample. And he said clearly 2 out of 6 could tell a difference, therefore this compound's important. Now, is anybody troubled by 2 out of 6 choices when there's 3 samples? It again amazed me, and the room was full of sensory scientists too. And not a person raised their hand because the probability of choosing 2 is really, really high. By total accident, the probability. And so it was interesting. Nobody said a word about it. Let it go by. And again, there's been some paper. Sensory is not my bag, believe me, but where they were talking about the brain filling in for a missing compound. If you have some perception, this is a flavor, and you leave out part of it, your brain may fill that compound in even though it's not there, and so you still perceive things. So, again, how do you work with these things? One of our problem always is the darn brain. It messes things up. It would be nice if we could just have some limit and say we need so many parts per million of this, and that would be important. But we just don't have that kind of information. And again, like I say, there are many different procedures, bitter compound storage of linseed oil. There's a little different one where methanol water extraction, linseed oil. So this wasn't a case where you're doing a water extract and looking at molecular less than 2,000. So extracting from linseed oil. They did do methanol water, though, assuming that the bitter compound is going to be more water soluble. Methanol water extract takes the dryness, sensory analysis. Bitter was found in that extract. Solid phase micro extraction for initial isolation, direct LC-MS fractions after reconstitution water tasting them. And again, found fractions in there that had bitter components, which then were identified. So there's a lot of, like I say, a lot of similarity in terms of methodologies for these types of compounds. But you can go through them, tingling components and black pepper. They all are extremely similar in how they go about the taste compounds. This comes out of, again, Debbie Peterson's research here on whole grain wheat bread crust. Again, the premise is that whole grain isn't consumed because of bitterness. People are sensitive to bitter. How do you get away from bitter? You load it up with sugar. Loading something up with sugar isn't necessarily the most nutritious way to deliver, a food component. So there was an interest in saying, what is the bitterness from the whole wheat bread? Is there a way that you can get around that to change how it's formed and eliminate it? And so this was a fairly long step. There were 6 different steps in terms of isolating bitter compound from whole grain baked bread, obviously. And it started off with hexane fractionation. Well, there wasn't any bitterness to that. The show it wasn't soluble in hexane was judged as bitter. Aqueous ethanol fractionation, then there's a hydrophobic fractionation, hydrophilic. Came down with the hydrophobic fraction, ultrafiltration, so do some size separation here. In the molecular weight less than 1,000, was judged as being bitter. So it's really guided by sensory. Okay, I'm trying to follow. We're doing different fractionation processes and try to follow. And finally, we get down to 2-dimensional chromatography. So a lot of isolation, a lot of fractionation. They came up with compounds that are bitter. And these compounds have been identified. It's interesting that they're not typically identified as bitter compounds in some of these research study foods, but they're found in all kinds of other sources in the literature, oftentimes traditional medicine products where people are looking at these types of compounds. And so, again, a nice piece of work where a number of the bitter compounds were identified. I'm not sure if that permitted them to make a good tasting or non-bitter whole wheat bread, but they can say where it comes from, what are the pathways, and it is through the Maillard-Browning reaction of forming bitter components. I kind of have gone through what are the approaches and their flaws. We certainly need help in terms of determining what's significant and what isn't from a sensory standpoint. That isn't easy. Well, I got done with that a little bit earlier. We could do 20 minutes of enzymes, 20 minutes of emulsions. We should probably do 20 minutes of emulsions. I don't want to cheat you out of your tuition. Okay. You're thinking, go ahead. Okay, that wasn't supposed to give my dogs. That was supposed to be the next presentation. Aha! Okay. I set my sights low. Okay. Emulsions. So there's a little bit of an introduction to emulsions, and then we're going to take a look at those that are specific to flavors. And so I expect you're all familiar with emulsions. I don't know how much you've worked with them. Sometimes the emulsion may be a curse for you, a problem in your work, and sometimes it's something you strive to form. For us in the flavor business, a lot of our flavors can be sold as emulsions. And there's no cheaper solvent than water. Do you want to use ethanol? Do you want to use vegetable oil, propylene glycol? Or do you want to use water as a solvent? Water's cheap. So you make your flavor as an emulsion, and water is the solvent for it. Emulsion, by definition, 2 immiscible liquids, one existing as particulate, others continuous phase. Particle size generally ranges from 0.1 to 100 microns in diameter. That's somewhat of a flexible number. The big topic these days are nanoemulsions. That's what interests a lot of people. And again, definition of a nanoemulsion just means it's a smaller size. So this is 100 nanometers, and you get down to about less than 100 nanometers. I call that a nanoemulsion. Some people say 200 nanometers is a nanoemulsion. I like 100 nanometers or less. And we'll spend a little bit of time with that later on. We have 2 different types of emulsions, oil and water. So talk about 2 phases, oil and water. Oil is the dispersed phase, so droplets. We have droplets in oil, and continuous phase. mayonnaise, milk, cream, flavorings, clouds, dressings. You know, cloud is an emulsion. It's not up in the sky. Okay. Anyway, clouds, dressings, so on. So oil and water, droplets, oil and water. Water and oil, you got droplets of water. And oil is a continuous phase. Butter and margarine are two food products we come across that actually have droplets of water, and oil is continuous phase. We've got different types of emulsions. They tend to be minor. Multiple phase, multiple layer emulsions. Multiple phase, oil and water and oil. We have droplets of oil and droplets of water in the continuous oil phase. So it's interesting. We have emulsion inside of the emulsion dispersed in the continuous oil phase. And it could be not oil, water, oil. It could be water, oil, water as well. But anyway, we have droplets in one phase inside another one. That's the droplets in the other. Multiple phase, multiple layer. And so we oftentimes think of this emulsion being stabilized by some kind of a layer that electrically repels or physically repels other droplets from coming together. We oftentimes think of that as being a single coating around that. But actually, you can put multiple layers of coating around each droplet. And so we intentionally put one layer around an oil droplet and then another layer to give greater stability. So we don't get them coming together, coalescing, and phase separation out of the process. So, again, different styles. Like I say, nanoemulsions, they're just tiny emulsions. We'll use different terms. Dispersed phase, discontinuous phase, internal phase are terms that we commonly use. Dispersed, that's the oil. In most cases, oil and water. Discontinuous, sure, that's the oil and water internal phase. So these are all the same. Continuous phase, external phase, so that's typically water in our case. Concentrations generally discussed as phase volume fraction. So how much of that emulsion is oil, how much of that emulsion is water. So basically we talk about the volume of oil, volume of water in an emulsion. Process of converting a two-phase system, an emulsion is done through a homogenizer, typically a mechanical process. You've all made the emulsion in a mixer, and a blender, and a homogenizer, and in some piece of equipment. It's typically done by mechanical processes, so high shear, ripping droplets apart, and then stabilizing those droplets when they've been ripped apart. There are different ways of doing it, but typically in the food industry, we do this. We break these oil, typically oil droplets, through high shear. High-speed blenders, high-pressure valve homogenizers, colloid mills. We have a device called a microfluidizer. Microfluidizer will give you about 26,000 psi. You get a good deal of shear in that type of homogenizer. They're inherently unstable. There's absolutely no question they will separate. The question is, can you keep them together long enough to suit your purposes or needs? But oil and water do not mix. They're different densities. They will separate eventually. So they're thermodynamically unstable. We just try to stable them long enough to be successful. Kinetic stability can form metastable systems stable for some time, and that's what we're doing. And again, we work with an emulsifier, and time is, can we keep this stable long enough? Our emulsifiers are really surface active agents. They absorb onto the surface. I'll always talk about oil and water. That's by far the most common. Can be the other way around. But anyway, whatever's the droplet phase, emulsifiers go to that droplet's surface, and they reduce the surface tension. They reduce the driving force to throw this out of solution. And so surface, whether it's a tween, whether it's a protein, whether it's a gummification, whatever. So these materials go to the surface, and they tend to stabilize that droplet. Typically, they're amphoteric, polar, non-polar. They may well have electrical charges to them too. What's a better way to keep droplets apart than have them have electrical charge? The negative charge, they'll repel each other. They won't come together. And as long as the droplets stay separated, they're going to be much more stable than if they coalesce. They'll rise much more quickly. Stabilizers, there's a difference between an emulsifier and a stabilizer. An emulsifier stabilizes the droplets and keeps them from separating. A stabilizer thickens the solution so they won't tend to separate. So they don't go to the surface. They make the solution so thick it won't separate. How about the butter is a good example, or margarine is a nice example. That's stabilized by thickness, by viscosity. As soon as you melt that butter, you melt that margarine, it separates into water and oil. Keep it thick enough, it doesn't separate. And so that's another way that we deal with it. You look at your salad dressings. Most of them are fairly viscous. Some aren't. Most of them are. And so if you can make a system viscous or a partial gel, then it's impossible for the droplets to coalesce, come together, or rise to the top. Oil and water emulsions, hydrocolloids, proteins work very well for that. You want some kind of a barrier to separation. Oftentimes they give you kind of a diagram, an energy diagram, where your system, you have high entropy, and so your system is here. Emulsions are not stable. You have too much interface. The interface of oil and water is not a stable system. Nature wants the two to separate, the oil on top, water on the bottom. And so what you want to do is you want to put some barrier in there, because these are high energy systems. You want to put some barrier to them coming together and dropping down to separation. So our goal is to keep the system up here and put a barrier to their particles coming together. So again, minimizing your delta G term and increasing the barrier is basically what we want to do to stabilize the system. We look at how systems become unstable. There's different mechanisms. Creaming is certainly a common one. In this case, these oil droplets should be dispersed. They'll always say oil. But the oil droplets should be dispersed throughout the whole sample. But oil is lighter than water. It's going to rise. It's going to float. And so this is called creaming. The particles haven't dropped. They haven't broken. They haven't come together as a liquid layer. But they're simply rising to the top. Cream separation on this example. We don't tend to find cases where we get sedimentation. Most of our systems are oil and water. Oil is lighter than water. It's going to float. And so you see this seldom, if ever, we see this. But sometimes these systems, if they don't have a good repelling from each other, the droplets will come together, and they will then form a flocculus. So this is now a bigger complex particle. So these are bonded together. And they rise and separate. It's interesting, they rise and separate much faster because they're bigger. The bigger the particle, the faster they'll cream, the faster they'll separate. These guys will be fairly slow, but the bigger they are, this one will go to the top much faster than that one. This is much bigger than this, and so these will separate even more quickly, cream more quickly. Coalescence is when the droplets actually come together. So maybe, you do this one. So maybe this barrier breaks and these two come together. The barrier breaks, comes together. So what you get is small droplets coming together and form big droplets through coalescence. And again, the bigger they are, the least stable they are in terms of creaming. Again, just some terminology. There's your droplet. Again, this is the interfacial region. So if we say this is oil, this is where oil and water meet. It's a high energy barrier. So it's continuous phase. That would be water droplets and oil in the system. So the interface is where a lot of the activity takes place. That's of concern. Dispersed phase volume ratio, different ways. Again, volume fraction. And so we look at ratio of two different phases. It could be mass fraction. So we'll typically talk about volumes of droplets, volumes of continuous phase, and more so than mass. Oops. Particle size distribution. Particle size critical, determining stability. and functionality. I think we'll have some slides later on about unique flavored emulsions that are nanoemulsions. The industry would like to have clear emulsions. Emulsions around 1 micron oil droplets in water, they're cloudy. They're just like milk. But if we want to have something that looks light and refreshing, like mouthwash, like a clear beverage, we'd like to have those particles so small they're clear. And so there's been a lot of work to try to make nanoemulsions that are so tiny, say that they disappear. They're cloudiness. But if we're looking at something and we want to make an emulsion, that's cloudy. And again, I think I mentioned that. If you want to make a beverage and you want it to be cloudy, you don't necessarily want to use real fruit juices because fruit juices precipitate the insoluble materials, they're brown, all kinds of problems. So what the flavor industry does, they make an emulsion, they make the droplets about 1 micron. It looks just like it's fruit solids in it. And so they're not fruit solids, they're just an emulsion. So emulsions are made for appearance in some food products. They can carry flavor as well, but for commonly they're made for appearance. In terms of particle sizes, you like a monodispersed system. You like all of the droplets to be the same size, much less driving force, more separation. Larger droplets will separate more quickly, and so this tends to be a more stable, more consistent system. But this is generally what we get, something that's more mixed in particle size. Expressing particle size is always a challenge. If they're all the same size, all uniform, that wouldn't be a problem. But there always is some size distribution, range in size. And you have to be careful when you give a particle size distribution, or mean particle size, I suppose I should say. Are you talking about based on weight of droplets, number of droplets, area, surface area? There's all kinds of different ways that you can calculate a mean particle size. In some cases, you're interested in what's the mean particle surface. You might be interested in covering a surface with an emulsifier. Sometimes you're interested in for different reasons. So again, you have to be rather cautious about when you see a number for particle size, what's it based on? Based on the number of particles, the volume of particles, surface area of the particles, or so on. Interpretation of mean diameters. If there were n equal sized droplets, the sum of the particles in distribution. A D10, we're looking at diameter measurement. D20, if they give you a mean diameter 10, it's based on diameter, mean diameter. Mean surface area of all these droplets, the volume, diameter, based on volume of particles. And again, some other combinations, volume, weight, and so on. So I guess my only point is if you get a list of mean particle size, there's different ways that it's calculated. And again, methodology gives you, method of analysis gives you different means. Imaging, if you do it a microscope and doing an analysis of an image, computer image, that gives you a D10. Digital imaging can give you a surface, electrical resistance in D30, D43. So you can have exactly the same emulsion giving you different numbers, depends upon how you measure that emulsion, how you measure that particle size. And my comment there is what method does your customer use? The customer will specify that your emulsion must have a certain size to be acceptable. They won't buy it otherwise. Well, you get very different numbers. Depends upon what method you use to measure the emulsion. And so what method you use, the same as your customer uses. Form emulsions, you do that through energy, high shear, interfacial forces. So you basically said you want to rip those particles apart and stabilize them once you get them ripped apart. Lowest energy, we have is two separate phases. So that's our lowest energy system, oil floating on top. And that's not a stable system. And so the droplets are spherical. That's the lowest energy state. So we do have all these spherical droplets of either oil or water, depending on how they And again, the smaller the particles, the higher the energy in the system. To break a droplet in a smaller droplet, one must put an amount of energy into the droplet that exceeds a less pressure cohesive force. So this basically tells you something about the shear that's required. And so as the particle gets smaller, it takes more energy to break them down. And so if we were going to use a homogenizer, we might use 2,000 pounds per square inch pressure. That'll give you a certain particle size. If you want smaller, okay, 5,000, 10,000. But there's a relationship up here about how much energy it takes to break a particle down smaller. And that's why with our microfluidizer, we can put 26,000 psi. We've gotten down to about 50 nanometers. That's the smallest particle we've been able to produce. That isn't clear yet. If you want it to be clear, you've got to be someplace around 10 nanometers. And you can make something that's actually clear. It doesn't reflect light at that point. The particles are too small. So particle size, like I say, requires energy. The bigger the energy, the smaller the particle size distribution. We break the droplets into pieces, but then there's always an issue of perhaps they're in the same neighborhood. Will they come back together? And so the idea of breaking them apart and keeping them apart is extremely, extremely important, and is part of the process that we use. We want oftentimes a small molecular weight emulsifier, something that'll come to that new surface. We rip the particles apart, we've got a new surface. We want an emulsifier that will cover that surface quickly so they won't come back together. And so your emulsifier gets to be very important in that whole process. And that's one thing where we suffer from. For our business, we tend to use an emulsifier that are modified starches. That's most common for us, or gum acacia. And they're large molecules. They aren't like some of the molecules you can do in pharmaceutical or other areas that are very, very small molecules. They migrate very quickly to the surface. They cover a surface very quickly. Our larger molecules won't come to that surface that fast. And that's why, it's one reason why it's hard getting a nanometer particle size for these droplets. Our large emulsifiers just don't suit us well. Emulsifiers, what's their job? One of the jobs is to reduce the interfacial tension. So you've got water in contact with oil. That's a high energy system. Let's make that oil surface appear more like water, and that reduces basically the energy difference, interfacial tension. Interfacial tension reduces energy to break drops, forms a protecting coating around the droplet, which then gives us some stability to that particle. There must be a sufficient emulsifier to coat the surface droplets, and so you need the right amount of emulsifier. The smaller the molecules, the smaller the droplets, the more emulsifier we need, because we have greater surface to cover. Faster the emulsifier moves in the surface, less coalescence. That's just what I mentioned. Probability of emulsifier being absorbed with droplet surface on contact. So emulsifier may not be as strong. We want to get that surface in the same way. That slows the movement of the emulsifier, slows the protection of the surface, results in poor emulsions. Amount of interfacial tension lowered by the emulsifier in another role. Effectiveness to form a membrane are all factors. Let's call it quits here. That's enough for tonight. There are only 2 more slides, really? Oh.
Sorry.
You're right. That's no fun. Okay. Okay, types of homogenizers. High-speed mixers, colloid mills, high-pressure valve homogenizers. And I think the next one shows these different pieces of equipment. Ultrasonic homogenizers. Microfluidizers are, like I say, one thing that we have that's really very high energy. Membrane microchannels. You can actually do better with membrane microchannel homogenizers in terms of particle size distribution. You force your particulate phase through a membrane, and the pores in the membrane, are very tiny. You get little, small drops that come out. The problem is in our business, we may want to produce 1,000 pounds an hour, and you don't get those flow rates through the membrane. So I'm not aware that we use membranes to form emulsions in the food business. We tend to use, for the most part, high-pressure valve homogenizers. They tend to be the most common for what we do. And this is just gives you an idea of what kind of particle size do we tend to get. So particle size here. Membranes, we get down here to a very, very small particle size. They're by far the best in that sense, but like I said, they don't have the capacity. Microfluidizer, we're good here. Again, very low in particle size. Here's colloid mill, good for the upper particle size. High-speed blenders are pretty visible. Oftentimes in the lab, people will pull out a blender and want to make the emulsion. That's not the best way to do it. High-pressure valve, again, works quite well. Ultrasonic also tend to work. Glucose really different types of homogenizers. So this I love, but like I say, it doesn't have capacity. This has pretty good capacity and still gets us into a very small particle size. Okay, now, okay. Come on over to the lab